Okay, so to start this video off here, we're going to go through an example relating to the current that we talked about in the previous video. So this example here, at time t equals 0, the charge in a wire is 2 coulombs. At t equals 300 seconds, the charge in the wire is minus 4 coulombs. So the charge has changed. It says for us to compute what is the current in the wire, and then assuming positive current flow is to the right, what direction is the current flowing? So the first part here for this is a very straightforward computation, because all we have here is, remember, for this course we're defining our current as the change in charge over the change in time. And so this would be minus 4 coulombs minus 2. Well, here, let me go ahead and write the formula down here. This is Q2 minus Q1 over T2 minus T1. So this again would be minus 4 minus 2 over 300 minus 0, which gets us minus 6 over 300, which, I mean, I could do this in my head, but I always like to make sure I don't make silly arithmetic mistakes. This is going to be just give me a 2 here. And if you do this in your calculator, a lot of your calculators can already put it in engineering notation for us. And so we get minus 20. The engineering notation would be milli, so we get minus 20 milliamps. Okay, so now what we're saying is, this is essentially kind of for the first part. For the second part, let me draw a wire here. Now, what the problem says is it's defining that this direction is positive current flow. So if the current here is negative 20 milliamps, that means the current is actually flowing in this direction here. Because if positive current flow is to the right, then negative current flow is going to be to the left. So the current flow is to the left. And that's the thing that's nice about current, is it's basically one direction's positive, the other direction's negative. So, you know, if positive current flows to the right, then negative current flows to the left. So since we got a negative number, we get that it's flowing to the left. Clearly, if I had gotten a positive number, it'd be flowing to the right. Now, just to make sure we understand this here, with one more quick example, let's suppose I have a wire here, and I have a current here that I'll call I1, and then I have a current going here called I2. And I'm going to tell you that I1 is equal to 6 amps, which, as a side note, is a lot of current. What is the value of I2? Now, the key thing to remember is, again, because of conservation of energy, I can't suddenly have this current, the magnitude or the value of this current being any different. So in other words, I2 still has to be 6. It's just a matter of whether it's positive or negative. So we know that I2 still has to be, I'm going to leave myself 6 here. Now I just have to decide, is it positive or negative? Which one is it? And again, this is not supposed to be difficult. It's going in the opposite direction of I1. And since I1 was positive, we know that I2 is negative 6 amps. And it's important to recognize, because this is just a very important concept to recognize, that, you know, as long as you just draw in the opposite direction, all it does to the current is make it negative. Because we'll use this in analysis techniques, and it's also useful just like, so if you get a negative number as an answer, you could say, okay, well, yeah, it's negative, but if I flip it the other direction, it would be positive. All right, so let's talk a little bit about voltage here. So voltage, there's a lot of ways that people try to explain something here as far as what voltage is. And voltage obviously has plus and minus signs, has polarity and things of that nature. But I like to kind of first get us an idea of voltage. First off, voltage is always measured with respect to another terminal. Now, one common one that we measure it with respect to is ground, but we don't always measure voltage with respect to ground. But that is one that we typically, and ground, as a side note, ground is 0 volts. We just define ground to be 0 volts. All right, so voltage is always measured with respect to something. But what is voltage? I like to think of voltage, and this isn't necessarily the best way or the only way to think of it. I like to think of voltage, and this is even what it's kind of defined as, is potential. And I'll put in parentheses here. I'll almost think of it as kind of potential energy. And the way I like to think about this, and you'll have to forgive my terrible sketching skills here, is that I have a water tower here. And out of this water tower, there is a pipe. And this pipe is going to feed our water system here. So this is a pipe here. And so what I have here, and of course this is my ground here, pipe goes underneath ground kind of thing. So what I have here is of course some water in this thing here. Now, because this is above ground, and if you've ever used a rain barrel, you will know exactly what I'm getting at here, is that because this is above ground, it's going to exert some pressure on the water in this pipe, and it's going to kind of force this pipe to move. And so let's say here, we're kind of trying to measure, we'll say this is my positive, and this is my minus, and then in terms of this, we might measure this as far as like the height. Maybe, and I'm just throwing a number out here, maybe this is 100 meters. So that isn't obviously a voltage, but it's the idea that, well, because that water is 100 meters up in the air, it's got a certain amount of potential energy. It's got a certain amount of way it can force the water down. But we should understand that if I increase the height of that to, let's say, 200 meters, I'll have more pressure being able to force more current down through this. So that's the way I like to think of voltage, is it has some kind of ability to store potential energy for us. And so we can use it kind of force, and if you want to think of it, this water you can kind of think of as current going through the pipe. So current going through the wire. Okay, so that's how I like to think about voltage. Now, when we think about voltage here, again, if we have some kind of terminal here, so this is some kind of either device or circuit. When we measure voltage, there's always two terminals that we measure voltage with. And we have plus, minus, and I'll say V. So voltage is always measured with respect to two terminals. Now, we'll get both a positive or a negative voltage, so we can get both positive or negative voltage, and it honestly does matter how you connect your device up. If you've ever measured, for instance, the voltage of your car battery, or if you've ever measured the voltage of just any battery, you typically, your voltmeter typically has a red and a black wire, and if you're measuring the voltage, you typically put the red one on positive and the black one on negative, if you know if you're measuring a voltage. You don't have to do that, of course, but that's what you typically do. But if we look at a device here, and I'm going to, again, put two terminals here, plus minus, and I'm going to say V1, and then I'm going to do plus minus V2. Now, here, if I say that V1 is equal to 10 volts, then V2, well, the value is going to be the same. The only thing that's different is that this is negative 10 volts for V2. Now, the other thing that is useful to remember is that when we look at these here, because we're also going to have current now that we have to think about. So you have plus minus V1. And again, we'll just let V1 be 10 volts. We typically think of the current flowing into the positive terminal. It's not that you can't think of it flowing into the negative terminal, but that's how we normally think about it, is that current is flowing into the positive terminal. Okay? Now, I know this is kind of a little vague with the voltage and everything of this nature, but most of the time we'll be either measuring or just computing the voltage. There is a much more technical, scientific definition for voltage that we are just not going to cover in this course because it doesn't really serve us any useful information. I think just having this kind of visual picture of potential energy for voltage is good enough, and it kind of gives you a good intuition on what voltage is. Which to kind of even further that idea of potential energy, let's even go back with one more example here to kind of illustrate this. If we're talking about static shock, and again, apologize for my sloppy drawing here. Let's see a doorknob here. And then you've got a finger, and you've got some static charge on that finger. Well, actually, the electric shock does not happen when you hit that doorknob. It actually happens right before it, and there is basically, well, let me draw this, like a lightning bolt. And it's not a lightning bolt, but I'll just kind of think of it as a lightning bolt here of static shock that, or electricity that goes from your finger to the doorknob. But it actually occurs before you touch the doorknob. And when you do that, the voltage of that static shock there is actually well over 10,000 volts. And so that's why, because it's such high voltage, and that's why they say danger high voltage, is that when you have high voltage like that, you know, air is not normally conducts electricity, but because there's such a high voltage difference, potential difference, it's saying, well, hey, I don't care about the fact that air doesn't conduct electricity. I'm going to ionize that air and conduct electricity through it. So we have something being very high voltage. All right, last thing we want to talk about here is power. Now, power, fortunately for us, is just a simple definition here. So power is defined as P is equal to voltage times current. So power is equal to voltage times current. And we remember that the units for this are watts. So power is basically a measure of energy transfer. In other words, if you do all the unit cancellation here, which we're not going to do here, is you would have energy over time is actually what a watt is. The amount of energy you're delivering over time. So that's what a watt is. It's how much energy is being either delivered or absorbed by it. Now this is very important for this V times I computation here. Let's just do an example to illustrate this here real quickly. So when it's doing that V times I, first off, it's thinking that if I've got a device here and I have plus minus some voltage 1 here, that the current I1 is flowing into the positive terminal here. So V1 is flowing in, the current is flowing into the positive terminal of this voltage here. So let me give you some numbers here. I1 is equal to 2 amps and V1 is equal to 3 volts. So the power would simply be 3 volts times 2 amps, which would be 6 watts. Now, we don't obviously normally write the positive sign there, but I want to emphasize that's positive. Because this is positive, this means the device is absorbing / using power. All right, we're going to talk a little bit more about this in one more lesson here and with some examples here.